A small piece of material the size of an apple can release an energy capable of destroying an entire city. How is it possible that something so compact has such an enormous power? To understand it, we will travel from the mines where this material is extracted to the facilities where it is transformed into one of the most lethal weapons ever created, the atomic bomb. The journey begins deep within the Earth, in remote mines in Kazakhstan, Australia, or Canada that produce 70% of the world's uranium. This metal is found in minerals such as uraninite or pitchblende in concentrations of barely 0.1 to 2%. The mines can be open-pit excavations with colossal machines that remove tons of rock, or underground tunnels that descend hundreds of meters. In some cases, in situ leaching is used, injecting sulfuric acid or carbonates to dissolve uranium and extract it without disturbing the surface. In processing plants, the ore is crushed into fine particles and mixed with acids in stainless steel tanks. This process separates the uranium, resulting in a bright yellow powder known as yellow cake, a uranium oxide with 80% purity. This step is carried out with the appropriate safety measures. Although radiation is low, constant exposure can be harmful to health. But yellow cake is only the first step. Natural uranium contains only 0.7% uranium-235, the isotope needed for nuclear fission. For a bomb, at least 80% uranium-235 is required, leading to the enrichment process. To do this, yellow cake is converted into uranium hexafluoride, a compound that becomes gaseous at 56 degrees Celsius. This gas is injected into high-tech centrifuges made of ultra-resistant steel or carbon composites that spin at more than 50,000 revolutions per minute in vacuum chambers. The centrifugal force separates the lighter uranium-235 from uranium-238. This process is repeated in cascades of hundreds or thousands of centrifuges, each one refining the uranium a bit more. Seismic sensors and control systems monitor each machine, since an imbalance of milligrams could destroy them. A single centrifuge can process tons of gas per year in facilities that operate non-stop for decades. But there is another material with power equal to or greater than uranium for constructing an atomic bomb, and that material is plutonium-239. But this element is not found in nature. It is produced in nuclear reactors by bombarding uranium-238 with neutrons in a slow and controlled process. The plutonium is extracted through chemical reactions in shielded facilities with lead containers, as its radioactivity is extremely dangerous. Both uranium-235 and plutonium-239 are the fuels of an atomic bomb, but their power only comes to life on the production line. Building an atomic bomb is a process that requires almost obsessive precision, carried out in secret facilities known as nuclear complexes. These factories, protected by concrete walls and military security systems, operate under strict protocols to handle radioactive materials and ensure that each component functions perfectly. The bomb's core, whether uranium-235 or plutonium-239, is the heart of the weapon. In a gun-type design, like Little Boy, the uranium-235 is melted in specialized furnaces at more than 1130 degrees Celsius and molded into two pieces, a cylindrical bullet and a ring-shaped target, each weighing about 30 kilograms. These pieces are machined with diamond tools to achieve micrometer precision, since any irregularity could prevent the chain reaction. In an implosion design, like Fat Man, the plutonium-239 is molded into a hollow sphere coated with a thin layer of nickel to protect it from oxidation. This process is carried out in sealed chambers with robotic arms because plutonium's radiation is intense. Each piece undergoes X-rays, laser scanners, and spectrometers to detect microcracks or impurities with tolerances of thousandths of millimeters. In the gun-type design, the two pieces of uranium-235 are placed in a reinforced steel tube inside the bomb, separated by a precise gap. A conventional explosive such as cordite or HICE is installed in an aluminum casing to propel the bullet toward the target at hundreds of meters per second. This mechanism is assembled on an automated production line, with stations where technicians in anti-radiation suits connect electronic detonators using millimeter-calibrated tools. Each connection is verified with ultrasonic sensors to ensure perfect synchronization. In the implosion design, the plutonium core is surrounded by a uranium-238 tamper that reflects neutrons to maximize fission, and a layer of high-precision explosives molded into lenticular shapes. These explosives made from compounds such as HMIIS are manufactured in specialized laboratories and assembled with tantalum and copper electronic detonators synchronized to microseconds. A neutron initiator, a small sphere of beryllium and polonium just a few centimeters wide, is placed in the center of the core to release neutrons at the exact moment. This assembly is carried out in clean rooms with HEPA air filtration systems, since a speck of dust could unbalance the implosion. Precision robots align each component, and simulation tests verify the uniformity of the shock wave. Now we move to a key part but rarely mentioned, the bomb casing, also known as the torpedo, due to its aerodynamic shape. For example, in the case of Little Boy, this casing was a high-strength steel cylinder alloyed with chromium and molybdenum. It measured 3 meters in length, 71 centimeters in diameter, and had a thickness of 2.5 centimeters. The steel, forged at high temperatures and machined with laser precision, weighed about 4 tons. It was designed to withstand intense vibration